today Professor Achim Roche from University of Cologne. Achim did his PhD from University of Karlsruhe in 1998. He was then a postdoc at Rutgers University from 1998 to 2000. Following this, he moved back to Karlsruhe as a junior group leader, and he was at Karlsruhe in this position until 2004. And since 2004, he's been a full professor at University of Cologne. So Achim Roche is a condensed matter theorist who has broad interests, and I got to know him, very early in my academic career through his very interesting work on non-equilibrium Kondo effect. This is the problem where you have an isolated spin and the question of how it gets screened by a free-forming gas. And because of experiments, everybody wanted to know what happens to the screening physics when the electron gas is out of equilibrium because of current flow. And so Achim did some beautiful work in this direction, got many people interested in this general area of ultimate equilibrium physics. And he has also done very interesting work in thermalization in cold atomic gases, hydrodynamic transport near quantum critical points, and more recently, this work that he's going to tell us about, fermion dynamics, has also got a lot of attention in the community. He's got two very prestigious prizes recently. One of them is the Leibniz Prize in 2013, and the other is the Europhysics Prize in 2016. So with this, I'm looking forward to this talk. Thank you.
Yeah, thanks a lot, Aditi. So it's my pleasure today to tell you a little bit about one of the stories we have been following in the last few years. And it will be a story about a special magnetic texture, as fermion. And I want to try to explain to you what that structure is, why is it interesting, and why it may have some application perspective, but why it also may be interesting from some more fundamental points of view. So let me start right ahead before starting right ahead, let me acknowledge my collaborators. And as Aditi said, I'm a theorist, but actually, as you'll see also in the following, the work is really powered by a very strong collaboration between theory and experiment. So especially the group of Christian Fleiter in Munich, but we also collaborated with a large number of other experimental groups. Today I also show some experiments by Peter Milde in the group of Lukas Eng from Dresden. Good, so let's get started. And so I'm a solid state physicist, and I'll mainly talk about a class of materials which is called chiral magnets. And luckily, there's only one thing you have to know about these materials, namely that their crystalline structure is such that it lacks inversion symmetry. So there's a left-handed version of this crystalline structure and a right-handed version, and they are different. Now, why? What is the main consequence of that? And that's also very easy. So you have now some structure with some handedness, and that means then it turns out that there's a force which likes to twist magnetic structures. So this force is called Dzerzhinsky-Morier interaction, and it says you gain energy when you twist a magnetic structure. It's a relativistic effect, usually small, but as soon as you lack inversion symmetry, you have this tendency. And the simplest consequence of that is instead of a ferromagnet where all spins point in one direction, you get a helical state where the spins wind slowly. Now, so the phase diagram of one of these systems, so that was kind of the historical first example, looks always the same. So here we have temperature, magnetic field, and when you cool down the system, let's say it's zero magnetic field, you get this helical state, which I already introduced, so a twisted ferromagnet. But actually, topic of today's talk will start from this small phase pocket. So there's a small range of temperatures and magnetic fields in this material, where you form a very peculiar magnetic structure, and we'll take a look at that in a moment. So it's if you like, you can think of it as a lattice of magnetic whirls. And so here it's a small phase pocket, but actually if you make a film of this material, even a thick film, then this extends up to lowest temperatures, and I'll show you later this exists also at room temperatures and where you like. Good. So what is this type of magnetic structure? What is the essence of that? And and for this, it's useful to view this from a viewpoint of topology. So, and it will be the topology of a hedgehog, or actually what works better than a hedgehog is actually the sea urchin here. So, so this is now the theorist version of a hedgehog. So we have a ball where spins point in all directions. So here the magnetization winds once around the unit sphere. And the only piece of topology we have to know is that you can't smoothly deform this structure into this structure. So that's not possible without going through a singular spin configuration. And that means, and in other words, this thing here is a topologically stable configuration. So what does this sphere here have to do with the magnetic structure we want to discuss? Well, for this, we start with our hedgehog, and we comb it a little bit, so this doesn't change topology. And as next step, we take it and project it to the plane. So the North Pole gets now to project it to the space at infinity. And this is precisely and this is the building block of the magnetic structure formed in this material. Yeah, so
pointing down in the middle and up at the
exactly. So we are pointing up at the outside, down in the middle, and then we smoothly connect in such a way that the whole sphere is connected. So each magnetization direction is covered. Yeah? And now we can take this building block and make a lattice out of that, and we can make columns of that, whatever you like. And one way to characterize this is so I said here so you see here the spins winds once around the unit sphere, and you can calculate this also in the plane by calculating this integral over the direction of the magnetization, and this is precisely the winding number, which is quantized to -1, so spins once around the unit sphere, and when you distort the system, then it remains quantized to this value. Good, so I already told you the name of this thing is Skyrmion, and that honors the work of Tony Skyrm. So this is a British physicist, and he made already in the 60s a very profound observation. So I think that's one of the highlights of theoretical physics. Namely, he considered such a topological defect, now not in 2 dimensions as I did here, but in 3 dimensions, and not of spins, but of pions. And he found out that the analogous topological defect has the property that it's actually a baryon. So that's surprising, you know, the pions are bosons. And it turns out if you make a knot in this field of bosons, what you get out is actually a field with completely different quantum numbers, namely a fermion. And if you like a baby version of that, we have here with our Skyrmion. So Skyrmions have a long history, also in solid-state physics. So in the late 80s, it was first suggested by Bogdanov and co-workers that one should look in such chiral magnets for such systems. But, and then they had an important role in understanding quantum Hall physics, but the type I want to discuss right now was first discovered in 2009. Good, here are a few pictures of Skyrmions. So first they were observed in neutron scattering, where you just see this perfect lattice of magnetic worlds in Bragg spots. But you can also take directly pictures. For example, you take an electron microscope, and then you can really image in real space how the spins. So here you can image the spins in the plane, and then you can see that they have this world pattern, and you see that it's really a perfectly periodic structure, which is formed here. And later I'll show you also some magnetic force microscopy experiments.
How do you know it has the right topological charge? I mean, you can't get all spin group components from these measurements.
Yeah, so from this measurement, you only have the components in the plane. Indeed, you need the third direction to get it right. So if you're very strictly speaking, you don't know it, but we know, yeah. But from this specific experiment, and I think, yeah, there are some STM experiments which actually get all 3 components by using tips with 3 different magnetizations and combining the pictures. But you're right, this experiment doesn't prove the topology, if you like, But even before these experiments existed, we were sure that this is the right one. We'll see later actually direct physical consequences of the topology. So will be good. One slide on the, so I don't say much about this. So one slide on the theory of skirmish formation. It turns out that the phase diagram I told you from theory is what you should get in all these in a class of materials. Whenever you have a magnet which is cubic, has no inversion symmetry, and if spin-orbit coupling is weak, then theory predicts that you always see the same phase diagram, and this is indeed what happens. So there are much longer lists than here of different systems where this has been seen. There are metals, semiconductors, insulators, thin film spike systems. Skirmins happen at low temperature, high temperature. You have then at 10 nanometer size, 1000 nanometer size. So they are everywhere. And so this was on chiral magnets, but actually, and that I will also discuss briefly more, there are also alternative systems which are based on ultra-thin magnetic films, and there you can find even smaller ones which go down to the size of 1 nanometers. And from the beginning, people thought about using these skirmins for applications. And I think the reason for this is rather obvious. Namely, you have something which is topological, it will have a long lifetime. And then I'll show you that these skirmins are the one magnetic structure which is most easily be manipulated by small forces from all the magnetic structures we know. And then there are a number of other properties which make them ideal candidates to build some type of memory technology out of these skirmins. And an early suggestion was by Albert Fair was to encode information in the distance of skirmins and then make various devices out of that. Now, if you really want to use skirmins, then you obviously want to have a list of properties to be fulfilled. So you definitely want to have them at room temperatures. You want to have a way to destroy and create them, and you want to control their motion in nanostructures. And I just briefly want to flash how these, to what extent, how far we are with that. So if I would have given you the talk 2 or 3 years ago, I would have said these are all open challenges. But that has now completely changed. So in the last few years, so the last 2 years, I should say, has seen many reports on skirmins at room temperatures. Actually the most promising family of materials is that you take layers of magnetic elements and heavy elements. So I told you this tendency to twist comes from relativistic effects. So you need some heavy elements to make this happening, especially if you want to have small skirmins. So what you can just do is you take, with standard industry-style processes, you take stacks of these types of materials. And indeed, by now, people can reliably generate skirmins in those in a large number of structures. If you use this structuring to design these relativistic effects by combining heavy elements and magnetic elements. And among these structures are also some of the smallest skirmins which have been observed. So that was challenge 1, skirmins at room temperatures, and that at least since 2-3 years, this is a solved problem and we have many materials. The second challenge is maybe more difficult one. You want to create and destroy those skirmins. And again, there are many interesting experiments. I show you the one which I find most exciting, which is a work by Roland Wiesendanger from last year. And what you see here, these bananas, is actually a picture of a very distorted skirmin. So it's the same beast, same topology. And what he was able to do is he took the tip of an STM and then he applied an electric field pulse. So not a current, but just an electric field. And let's say by putting a minus pulse, he was writing a skirmion and then it just stayed there. And by putting a plus pulse, he was deleting it again. You know? So in this, he could really step by step in a controlled way write and delete skirmons at hadad. And that's exciting. So I should say, I think it's fair to say that it's not fully understood why this works so well. And, but the exciting aspect of this is when you switch something with an electric field, you almost need no energy to do that. Yeah, so electrons are almost not moving. So this could be an extremely power efficient way to store information, much more efficient than today's technology. So I think that's a very promising direction. But there are also many other ways to create skirmons. And the nicest picture here comes from Los Alamos, from Argonne. Here you see an experiment where there's a constriction, and then the current is flowing through this constriction. And then you see how just like the soap bubbles, here skirmon bubbles emerge from this constriction. So to be fair, these are really big ones, so they are not the small ones which we need for applications, but it's nevertheless a nice movie showing that these structures can be easily created.
What are those little the things going up and down on the left?
So these are essentially domain walls. So these black things, or what is?
Oh, but the white things, is that like a corral or something?
Oh yeah, that's the nanostructure. So this is just the nanostructure. Now at least it's clear that we have skirmons at room temperature. We can create and destroy them. We have very first experiments going for nanostructures. So I think, and I think the field is now moving towards making really devices out of that. If you ask me whether this will be ever interesting for applications or whether it can really make money with that, I don't know. But with this, I also want to switch stop this kind of application perspective and want to switch gears. And I want to explain more first. Why are skirmons the one structure in nature, magnetic structure, which we can manipulate best with fields? I have one more application slide. Sorry for that. Okay, let me skip that one. And I'll tell you that the properties of skirmons are best understood using a language of electromagnetism, and not electromagnetism of magnetic and electric field as we know, but about some emergent electric and magnetic field which describe the coupling of the skirmons to electrons and magnons. And then we'll investigate what happens in a phase transition where we change topology, and I'll show you this will be a story on the physics of magnetic monopoles. Good. So let me start by reminding you about something from your quantum mechanics course, namely the physics of b.r.i.c.s phases. So b.r.i.c.s considered the following problem. There's a Hamiltonian quantum system, and I now slowly change my Hamiltonian. And I do it so slowly that the system remains always in the ground state. Sounds very boring, but b.r.i.c.s realized that it's not completely boring because a quantum mechanical wave function is also characterized by a phase. And we have to think what happens to this phase of this state lambda. And when you now compute the space for such a slowly changing quantum system, then you get a dynamical contribution to the phase. But then there's also the b.r.i.c.s phase contribution, and that's a phase which depends only on the way how you change the system, not how fast you do it, but just on which trajectory you change the system, and therefore this is called a geometric property. And so one example for such a geometric phase, which is not a Berry phase, but we'll see the relation in a second, is the Aronoff-Bohm phase you pick up when an electron moves in a magnetic field. So then you also pick up a magnetic phase, which does not depend on how fast you move in this magnetic field, but just on the flux which you enclose by motion. Good. And now we have to ask the question: what happens when an electron moves along such texture? And so the spin of the electron will adjust to the magnetic structure. So the spin will slowly change because the texture is very smooth. So the spin will slowly change, and it will pick up a Berry phase. And now we do the following trick. We just, and this is suggested by Wolowick from the late 80s, we rewrite this Berry phase as an Aronoff-Bohm phase. So we pretend that there's a magnetic field, an artificial magnetic field, and we ask ourselves how strong do we have to choose this magnetic field to describe the effect on the electron. And the Berry phase actually for a spin moving on a trajectory is just given by the area enclosed by the spin when you draw the spin as a unit vector. So we now have to translate this thing to a magnetic phase. And actually, for the theorists in the audience, or for everybody, let me just give you the one slide theory slide, how you can do this technically. So we have an electron which moves on some background, which is here described by the magnetization N. And now the only thing you have to do to get these Berry phases right is that you choose the quantization axis of your spin to be always parallel to this magnetization N. That's it. So here's what to do. You introduce some new fermions which have this rotated spin quantization axis. And then you rewrite your theory in terms of these new fermions. And what you get is a coupling of a current to a vector potential. And this vector potential is just this artificial electromagnetic field which keeps track of all the Berry phases. It's as simple as that, and therefore we can just write down a kind of dictionary where we translate the language of magnetization dynamics to the language of electrodynamics. So for example, the role of the electric charge is played by the question whether the spin is moving parallel or antiparallel to the magnetization. So whether you're in the minority or the majority band of your magnetic system, that determines the charge in this artificial electrodynamics. And then the role of magnetic field, that's taken over by the Berry phases which you pick up when you do a loop in space. And the formula is given here. And the role of the electric field is taken over by Berry phases, which you pick up when you do a loop in space-time. And so we can immediately calculate from the knowledge of the magnetization, we can calculate this electric field. And that works always, as you can see from this expression, but this magnetization is not collinear. So this is true for all magnetic structures which are not collinear, but now what is special for our system is this connection of topological quantization and these emergent electromagnetic fields. Namely, we said our experiments have a winding number -1 or +1, doesn't matter. This means in this language is that we have exactly one flux quantum carried by each fermion. So we have an emergent electromagnetic language, and the rule is very simple. Each fermion carries one flux quantum. Good, so that's theory. Now we want to see whether how this reflects in nature. So these are not real electric and magnetic fields. They are just bookkeeping devices for our Berry phases. But still, the electrons should see a force from this field, so it should be easy to measure these electric and magnetic fields by the force they give to the electrons. So let's take a look. So here is so how do we measure magnetic field? It's clear by a Hall effect. So here's an early Hall effect measurement, rho xy. And what is changed here is the magnetic field. And so we start from large magnetic fields. And then at this field, we enter the Skyrman phase. And you see there's an extra contribution to the Hall effect. And then at the second field, you leave the Skyrman phase again. It's switched off. And here you enter again the Skyrman phase and leave it again. So whenever you go into the Skyrman phase, you get an extra contribution to the Hall effect because there was an extra magnetic field. And indeed, for this material, which I'm showing you the results, these effective magnetic fields, so one flux quantum per Skyrman is 12 Tesla. So a pretty large field, which gives you a much larger than the applied magnetic fields down here. And this gives you a clear extra signature in the Hall effect. So this is nicely been seen. So now we get more ambitious. So we've seen the electric field. So we now open our textbook on electrodynamics and want to see something else. And obvious next thing is you want to see the electric fields. And so you think about Faraday's law of induction, which says when you have a moving magnetic field, so a moving Skyrman lattice, then this should give you an electric field. And the formula should just be given electric field is drift velocity by this emergent magnetic field. And that's also interesting if you want to detect the motion of Skyrmans, because now we know the size of this one. If you can measure this one, then we know the drift velocity. Good. Now, it's clear that this is not a real electric field, so you can't measure it directly. But again, you get a force on the electrons. They for example, in a Hall geometry, then they will be pushed to one side of the sample, and then this will generate a real electric field, and that you can measure.
Is there also a real Faraday effect if you change magnetic field in time? Does it generate electric field?
Yes, the answer is yes, but these Skyrmans are topological, yeah? So you can't easily just change. So they have one flux quantum per Skyrmion, so you can't change the magnetic field without destroying the Skyrmions. That we'll do in the last part of the lecture. Yeah? You'll have to wait a little bit, because that will be the story where the magnetic monopoles show up. Good, so back to here. So this is move essentially with the same velocity as the electrons are drifting at this current density. Because they're flowing with the electrons more or less. So it's now worthwhile to take a look at the numbers. So the current densities where this happens is 10 to the 6 amps per meter squared. And that sounds like a very big number, but it's actually not. So this is actually, you should compare this to the current densities one usually needs to do anything with magnetic structures. And usually you need 100,000 times larger current densities to do anything with the magnetic structure. And here, these Skyrmans really move with forces which are about 1,000,000 times or 100,000 times smaller than any other magnetic structure. So I think, so this is the one structure which you can most easily manipulate. And what is the reason for that? Well, it's precisely this Berry phase coupling. So we said that the electrons steer magnetic field, and therefore, when they flow through the system, there's a counterforce to the Skyrmion, which is the Lorentz force. And this is actually what the Skyrmans is driving about. There's another way to think about that. Namely, you can think about this, that around this, each Skyrmion you have a whirl of actually spin currents, and now you have an interplay of a uniform spin current which comes from applied electric current through the system with this rotating spin current, and therefore this force on the Skyrmion is sort of like is a quantum version of the usual Magnus force, which you, for example, get when you get a ball rotating and shooting it around the corner. And it's quantum version because actually around each fermion what you have is a spin supercurrent moving around. Good, so last look on this force. So this Berry phase coupling, the force from the Berry phase coupling can be written in this form. So it's like a magnetic field. And so let's take and this force also forces the fermions to follow the drift velocity of the electrons, and it's worthwhile to take a look at the prefactor. Namely, the size of the prefactor is actually given by this effective magnetic field which I discussed before, namely the flux quantum per fermion. That's the size that's the magnetic field an electron sees, but this is now multiplied by the number of spins which are inside the fermion. So in total, the effective magnetic field the fermion sees as a particle can easily be 100,000 Teslas or stronger, much stronger than any magnetic field you can generate in a lab. And so in insulator it's actually quantized. It's one flux quantum per atomic unit cell corresponds to the effective magnetic field our fermion is seeing. Good, and then we now can answer the question, why do we have this ultra small current density getting this thing moving? And the answer is, this is the one phase of matter which couples most efficiently by Berry phases. So all Berry phases conspire to get these guys moving. So we have an extremely efficient coupling by Berry phases. Then the magnetic structure is very smooth, so it doesn't pin easily to disorder. And there are also other effects which come from the fact that we move a lattice in a disordered environment, and as this structure is rather stiff, some effects of the disorder which try to hold the fermions also cancel out. But most important effect is this very efficient Berry phase coupling. Yes?
Is there a back action by the electron or the current to the fermion?
Yeah, the force which was driving this fermion is this back action. Yeah? So, okay, so good. So we have two effects. One is that the electrons feel an effective magnetic field. Yeah? So they go to one side. Then there's a counter force on the fermion. That's the first part. But then the fermion starts to move. Yeah? And we said, and then you can ask, how does this moving fermion now give a force on the electrons? And the answer is this emergent electric field. That's natural counterforce then when the fermion is moving because of this, because of the initial force. So it's like very similar to standard electromagnetism, and so it's also the same when you have a vortex in the current. That's all very similar physics after all.
And these fermions seem to be moving in millimeters per second, which seems like very slow.
Yeah, so it's very slow because we have the slow drift velocity of the electrons. Yeah? So when you apply if you use the current densities which you are applying in your experiment, which are a million times stronger, then the velocity is also a million times larger. So, but it's an important fact, indeed, if you want to make, so in some sense, having a small current density, so having a small current density sounds something super for technological applications. But for technological applications, you not only want to have small current densities, but you also want to move things fast. Yeah, and if you want to have things fast, then these currents are too small. So it's not true that these are a million times more efficient than your favorite systems, because if you could operate a fermion device with these currents a million times smaller than you operate your devices, but it would be so slow that nobody would be interested in it. Yeah? So there's no million times advantage of this, guys.
But you can drive these things much faster.
You can drive them much faster. There's also no Walker breakdown or anything. So as far as we know, we can drive them really fast also. There are also some experiments along that, but so we have these experiments which have reported 1 million times faster velocities than those I quoted here. Good. Can you say it again? So the subway was a bit too noisy.
What's the typical reaction time of your experiment?
Aha. So the question is on the reaction time. It turns out, so that's a good question. So the analog way to ask the question is, what is the mass of a skyrmion? Yeah, so mass is a property which says how long do you need to, how difficult it is to accelerate the system. And there it turns out that it depends very much on how you try to get the skyrmion moving. So when you do it like here with a current, the mass is essentially 0. So the skyrmion instantaneously follows the current. When you instead apply a magnetic field gradient, which also gets the skyrmion's motion moving, then the skyrmions have actually quite a sizable mass. And so they distort, and that takes some time to react to these distortions. So, but if you want to drive them by currents, it's extremely rapid. So it's essentially instantaneous, while with other probes, it's not instantaneous. Good. So let me show you one more example which shows with how ridiculously small forces one can move a skyrmion. And my favorite example for that are actually some of the first experiments ever done to image skyrmions have been done by the Tokura group, which looked with an electron microscope on the skyrmions. And what they found is then, let me just start the movie again. What they found is when they just put these skyrmions on an electron microscope, then they see actually that the pattern is rotating. It was kind of a ratchet type motion, but it was clearly rotating in one direction. And the question is, how can that happen? And the answer was that because of this electron beam, the sample was a little bit hotter in the center than at the edge. Yeah? And then there were some radial thermal currents flowing in the material to the side. There should be a simulation, but it's not so important. You can do this without the simulation. Yeah? And if you have this radial heat currents, then by the Magnus force, this gives you a rotational torque on the skyrmion lattice, and that makes it moving. Yeah? But I think it's a good example that, so just by looking at these guys, they start to move. It's so tiny are the forces which get these skyrmions moving around. So so we talked about manipulation of skyrmions by currents, and we found that the most natural language to talk about that is this of artificial electric-magnetic fields. And now I want to discuss with you something else, namely how can we change the topology? So what happens when we destroy skyrmions? And that will be a story on magnetic monopoles. So let me first introduce you to an experiment. So what we want to do is we want to destroy the skyrmion lattice and observe this with an electron microscope, with a magnetic force microscope. So this details don't matter. So with this electron microscope, you can just image skyrmions. So the lattice here is not so perfect as before. It's a more dirty system here, but you can nicely identify the skyrmions. And they are kind of metastable in this red region of the phase diagram. And now we want to destroy them and see what happens. And the way to destroy them is, for example, to reduce the magnetic field. And let's see what happens. So this was a picture at 20 millitesla. It's our skyrmions. And then we are at 10 millitesla. And then you see that these kind of lengthy objects have formed here. So it seemed that two neighboring skyrmions merged to this lengthy thing here. Yeah? So for example, these two guys merged to this object. And indeed, when you go on with that, then you see that you get more and more of these longer and longer structures. And indeed, you can convince yourself that locally the system tries to mimic what a helix is doing. So here's actually what you see is a piece of a helix where the magnetization just smoothly winds. So let's think about that, what we're seeing here from the viewpoint of topology. So first, what we are seeing is only on the surface of a material. So we have to think a bit what happens inside the material and what happens here to the topology, to these windings of the magnetic structure when we observe this thing. And first what we did is we looked at some numerical simulations and convinced ourselves that they not only reproduce the experiment, but also tell that whatever we see here on the surface also similarly happens in the bulk. And there's also some neutron scattering experiments which also confirm that whatever we're seeing on the surface is precisely what happens in the bulk. So that seems to be the same thing. Good. So let's think a little bit on this experiment from the viewpoint of emergent electrodynamics. So we said each skirmion actually is something which carries one flux quantum of emergent magnetic field. So remember, not real magnetic field, but emergent field. So this artificial magnetic field, which you use to keep track of Berry phases. Now, we change the number of skirmions, so we change the number of fluxes. And how can we do that? So obviously we have to change the magnetic field, and for this, it's most naturally that we need sources or sinks of this emergent magnetic field. So we need some magnetic charges to change the flux of the system. So that leads us naturally to charges of these emergent magnetic field, and these magnetic charges have the name magnetic monopole. So let me briefly remind you about what a magnetic monopole is. So magnetic monopole is a concept which was introduced by b.r.i.c.s, and he asked a very fundamental question, which up to now we don't have a good answer for. Namely, he asked the question, why is the charge of an electron and the charge of a proton exactly the same up to the sign? Yeah? So why do we get the same number out, despite the fact that we know a proton now? b.r.i.c.s didn't know that, but we know there's no proton is made of quarks, completely different stuff than the electrons, but still they have the same charge. How can that happen? And b.r.i.c.s suggested a solution, namely he said, let's assume that a magnetic monopole exists. And let's try to formulate a proper quantum theory of that object. And then he found out that this is only possible when charge is quantized. So if a monopole exists and we want to formulate a quantum theory out of that, then we only succeed if the charge is quantized. And the argument was the following. So you can think of a magnetic monopole to be the same magnetic. So magnetic monopole means you have a magnetic charge, so you have magnetic field going in radial direction. And now we all know how we can generate such a field configuration. We just take a thin solenoid. And at the end of a thin solenoid, we get precisely this magnetic field. Now this would be a true quantum particle if this solenoid, so the incoming magnetic field, would be invisible to all experiments. So then this would be a true point particle. And now you can convince yourself easily that the magnetic field inside the solenoid from classical physics you can never observe if it's sufficiently thin. But with the help of quantum mechanics, we can do an L.E.N.R experiment to detect the flux through this solenoid, with one exception, namely if the flux is exactly one flux quantum. So if the flux, this is the charge of this monopole, is just a multiple of an electric flux quantum, then this solenoid is then this solenoid is invisible. And similarly, if all the equivalently, if all the charges are multiples of 2 pi h bar divided of the charge of the monopole, then indeed to formulate the quantum mechanics enforces us that all charges are multiples of this combination of constants. So if you have a monopole, then we have solved this charge quantization problem. So that was b.r.i.c.s, and then there was certainly important follow-up work. For example, Toft and Polyakov found out that, let's say, in certain generalizations of standard models, magnetic monopoles naturally occur. And in the context of solid-state system, it was pointed out that one gets something like a magnetic monopole if you look at materials which are called spin ice, but that's something I don't want to go into. But what I want to discuss with you is now how we can describe our skirmion physics in terms of monopoles. You remember in the experiment we saw that two skirmions were merging into these lengthy objects. And now let's think what happens here from a viewpoint of electromagnetism. So we said this guy carries one flux quantum, this carries one flux quantum, and down here this object also carries one flux quantum. So what we have here, so in between when these guys merge, we have a singular point, and at the singular point, we make out of 2 flux quantum, we make 1 flux quantum, so 1 is lost. So we had a sink of magnetic fields in the middle. So we should think of this singularity, which will occur when these 2 skyrmions start to merge. We can view as a magnetic monopole, or more precisely, an antimonopole. So again, this is not a monopole of the real magnetic field and doesn't help us to solve the quantization problem posed by Dirac. But the statement is, when we create such a singular defect, then from the viewpoint of the electrons, it will look like a monopole. So they will feel the magnetic fields as if they were a real monopole, and they will feel the electric field if the monopole is moving. So from the viewpoint of electrons, this just behaves like a monopole. And now we can, now when we see in the experiment that these 2 guys merge to each other, then we now, if you take the 3-dimensional picture instead, then we can either view this as this antimonopole was now moving up to the system and flying out of the surface, therefore changing the winding number by 1. So there was an antimonopole flying out of the surface, or equivalently, a monopole could have flown into the surface, and again, this helped us to change the magnetization. So let's, so here is the magnetic structure around this point, and this is actually, what happens at this singular point is actually nothing that you have such a hedgehog spin configuration, so the spins winds around this point in all direction. And now, when this guy moves up and down, then it acts like a zipper which zips 2 skyrmions together or apart. So let's take a look at a simulation of that. So what we do is we just use a standard approach to simulate now the classical dynamics of this magnetization. So we simulate the precession dynamics, but includes also the effect of thermal fluctuations that's necessary to get this thing moving. And here is such a simulation. So, and maybe you just look on the surface here, and then you see that we start from these single skyrmions. And as we now change the magnetic field so that skyrmion phase is not good anymore, we naturally get these lengthy objects forming. Yeah? So like in the experiment. So that happens here on both surfaces. So we start from the skyrmion lattice. I guess simulation will start soon again. We can also start it again. We start from the skyrmion lattice, and then as in the experiment, we see the merging of neighboring skyrmions. Now what I've done for you is now, for the simulation, we've colored this singular spin configuration, so these monopoles and antimonopoles, hedgehogs and anti-hedgehogs, moving through the system in red and green. And you'll see that the green guys always fly from right to left, and the red guys from left to right. And the script of what you're seeing here is shown here. So here's time, and this is now the distance here from the surface, the layer, and red and blue are the world lines of these monopoles and antimonopoles. And for this simulation chosen here, I'll show you a second one in a second, they always come on the surface. And via this motion of these monopoles, we change the winding number here from, we start with 15 skyrmions, then we go to 14, 13, 12, 11, and so on. So thereby we reduce the number of skyrmions. And for example, what you see here, here a monopole and an antimonopole were meeting, and they were annihilating each other in a burst of spin waves. So a particle and an antiparticle, they meet, and then they annihilate and emit spin waves in all directions. And so that was that was for reducing the magnetic field. You can play the same game by increasing the magnetic field, and you get the same picture. Now the difference is here for these parameters, these monopole antimonopoles are mainly generated inside of the material, not at the surface. And so as you can expect, you get that they have to be created pairwise if you create them inside. So you create a pair of monopole and antimonopole, and then they fly apart, thus changing the magnetic structure.
Can you get fake diamonds as well?
Pardon?
fake diodes?
No.
No.
Okay, so let's say one thing which we can get is that so these monopoles they actually see a repulsive potential from the boundary. So sometimes what you get what is called so it has been called b.r.i.c.s by my colleagues. So you get a monopole which hangs at some distance below the surface in a metastable state, and just kind of is pinned to the surface, but can't make it through the surface or can't get fully destroyed because it's metastable. That's the kind of the state which that's one of the metastable states one can find.
Maybe I didn't.
Yeah.
So dione would be the one that would also have pure fake electric charge. Monopole, which would have the fake electric charge, would be a dione. So
yeah, no. That so in this approach the electric charge we get only when we have time-dependent magnetization. Yeah? So we get electric fields only when we pick up Berry phase in space-time. So we need a time-dependent magnetization, and here the internal magnetic structure of this monopole is fixed. So the only magnetic electric field it produces comes from the motion, but it has no static electric field. And I wouldn't know how to generate something with in this language at least, I wouldn't know to generate something with an electric field. So I would need something with a time-dependent. I would need something with a dynamical electric magnetization, which has more than the translation motion to get also an electric charge. I haven't thought about this carefully, but it certainly isn't known here. So let me just finish with one slide showing you that the Skermans which I've shown to you are not the only ones. So I told you another natural phase in the same type of materials are helices, and what one can also do is now one can try to embed a Skerman in a helical phase. That we did in some recent work, where you can now ask what happens when you try to put a Skermion in a helical phase, and that's how you would maybe do it naively, but that turned out to be a very bad idea. So what is actually topologically equivalent and has much lower energy is this structure. So this is a Skermion. And now if you put a Skermion in such a helical phase, then in contrast to the Skermions I have shown you before in the ferromagnetic phase, then you can also, and the anti-Skermion has exactly the same energy. That's just a shifted version of that one. And then, and then you can continue and form bound states of different Skermions and get multi-Skermion states. So that's something we are looking at right now. And all this, I should say, is also seen in the experiment. So you get these lines of defects like here. You get Skermion clusters like here, and you can find all these types of Skermion and anti-Skermion lattices in the experimental system. Good. Let me finish here. So I hope you had some fun with the Skermions. So when you start with these Skermions, magnetic Skermions, everybody thought that they're a super exotic object. But nowadays we know they are everywhere. So in all chiral cubic magnets, they are there for sure. But now they can be, by standard techniques, they can be easily generated in multi-layer systems by just stacking magnetic layers and heavy element layers on top of each other. We have them you can easily generate them in all sizes, at all temperatures, which you like. But I think the main source of fantasy for applications comes really from the fact that they can so easily be manipulated. So this is the one magnetic structure which we can best manipulate. And main underlying reason for that is indeed this perfect Berry phase coupling of the smooth magnetic texture to currents. I think that's the key for that. And then I told you a bit on some fun we had by thinking about what actually an experiment means, where we where we change the topology of the lattice, where we destroy and create skyrmion lines. And the natural language actually is the language of emergent magnetic monopoles. And yeah, with that, I would like to finish. Thank you.
Questions?
So with the monopole anti-monopole feature, it should basically make the thickness very small.
Mm-hmm.
So then there's really no space for them like to create what happens? Is it just going to be a continuous connection between the top surface and the bottom surface?
So you're asking when I make this smaller and smaller and smaller? Yeah, so if you make it smaller than the distance of the, so when I make it thinner and thinner and thinner, then it makes no sense to talk about the monopole. Yeah? Then kind of this whole thing goes back in one step. So then you should think about this as a two-dimensional system. You can still think about this. So you should rather, so theory language would be you have an instanton, so you have a singularity in space-time still, which says how this two-dimensional object goes away, but then this monopole would exist as a useful object to talk about that. So that's only when you have now these lines and you have a bulk system more.
So, in the very bottom there, you're starting to look like an L.E.N.R phase.
Say it again?
When your experiments are starting to merge, you're starting to look like an L.E.N.R phase.
Yeah.
What sets the, why are there bands included in thickness?
Okay, so one question is what is the length scale of this? So the distance of this. Or you ask the regions, the size of the regions in which this orders.
No, just the width of the blue thing.
Okay, so that's simple one. So that's the same thing which sets the distance of the skyrmions themselves. And so it's, if you like, the same as the radius of the skyrmion or the pitch of the helix in the system. And it's set by the ratio of spin-orbit interaction and exchange interactions. And so if the relativistic effects. And so from a very theory point of view, the dimensionals, it's fine structure constant actually which stands there. So it's so the width of this thing is in units of the lattice spacing is given by the ratio of exchange interaction and spin orbit interaction. That's a relativistic effect. So it's typically large and yeah.
And is there a constraint on how much glue you have to have? Because these long things could just collapse into surface.
Okay, so we are now so what we did here is we were driving the system into a phase where the true ground state is a helix. So a regular arrangement where we have helices. And what you see here at the bottom is a piece of a helix. So you can ask, a more difficult question is now on what time scales ultimately a proper helix will form. So on what time scale you get, so you should think of what comes out here, kind of yeah, so there are still a large densities of defects in this helical phase, and to eliminate those will take a much longer time than, for example, the simulations we're covering or also the experiment here was. So here in the experiment, it was actually frozen into a kind of classy state. What happens in the experiment is that this is frozen into a classy state because this order prohibits this to relax to the true thermal ground state at this temperature, which is would be a perfect helix.
These skyrmions form in antiferromagnets, and have they been observed in antiferromagnetic systems?
So first, so if you look at the phase diagram, what we always used is, or what we, in those examples which I showed to you, used, was this external magnetic field. Yeah? And the problem is, in antiferromagnets, we don't have the analog. We can't easily apply something which is analogous to a uniform magnetic field. So this says that it's much tougher to generate a skyrmion in the antiferromagnet. But this doesn't mean that they shouldn't exist. So they should also exist in antiferromagnets. And there are also cases for skyrmions where you don't need an external magnetic field. You can use anisotropy terms easily. So it's not a requirement, but it requires more fine fine-tuning of parameters. So antiferromagnets, you have to fine-tune things properly and find the phase, so it's much tougher and have not been seen. But I think they should exist.